In this lesson, we are going to see how we can apply our knowledge of polynomial division to come to an important conclusion about the relationship between the remainder and the divisor. Let's start by completing the division of this polynomial, p of x, by the divisor, d of x. I'm going to use synthetic division to make the process a little faster, but note that you could use long division if you prefer, and the steps for that are laid out in the graphic on the lesson page for this section. The divisor here is already in the x minus a form, with the a value being positive 2. So we'll write a 2 beside the half box symbol. Next, we write the coefficients of the dividend polynomial in the upper half of the box. They are 1, 1, 1, and 6. Then we drop down the first coefficient, the 1, to underneath the box, and multiply by the 2 to give us 2, which we write underneath the next coefficient, which is again 1. We then add the 1 to the 2 to give us 3, which we write underneath the box. The process now repeats. 2 times 3 is 6, and 1 plus 6 is 7. 2 times 7 is 14, and 6 plus 14 is 20. Now, interpreting our result from right to left, we have a remainder of 20, a constant term of 7, an x term coefficient of 3, and an x squared term coefficient of 1. Our quotient is then x squared plus 3x plus 7 with a remainder of 20. To summarize what we've done so far, we've taken our dividend polynomial x cubed plus x squared plus x plus 6 and divided by x minus 2 to give us this quotient x squared plus 3x plus 7 plus our remainder of 20, which is still being divided by the original divisor of x minus 2. Now let's manipulate this equation to give us the division statement, which tells us that the dividend polynomial p of x is equal to the quotient q of x times the divisor d of x plus the remainder r of x. We can get this form from the equation we already have by multiplying both sides of the equal sign by the divisor, x minus 2. Let's look at this equation more closely. The left-hand side is the dividend polynomial, which means that the right-hand side must also be the dividend polynomial, if we were to expand the brackets and combine like terms. Let's now evaluate the left and right-hand sides at x equals 2. Remember that positive 2 is the a value from our divisor, which has the form x minus a. When we do this, we see that the divisor on the right-hand side will evaluate to 0. And since it is being multiplied with the quotient we found earlier, it doesn't matter what the quotient evaluates to, since anything times 0 gives us 0. So that whole expression will evaluate to 0. This leaves us with just 20 on the right-hand side. Remember that 20 is the remainder from dividing our polynomial p of x by the divisor x minus 2. Isn't it interesting that p of 2 is equal to this remainder? Just to prove that this is the value of p of 2, or our polynomial evaluated at x equals positive 2, let's quickly evaluate the left-hand side of the equal sign. 2 cubed is 8, and 2 squared is 4. 8 plus 4 is 12, 12 plus 2 is 14, and 14 plus 6 is 20. As you can see, the polynomial p of x evaluated at x equals 2, or p of 2, is equal to the remainder when p of x is divided by x minus 2. This can be generalized by the remainder theorem. The remainder due to the division of a polynomial p of x by a divisor d of x of the form x minus a is equal to p of a. In other words, if we want to know the remainder from dividing a polynomial by some divisor of the form x minus a, we don't need to actually perform the division. We can simply evaluate p of a to determine the remainder. This is a very powerful conclusion and is useful when we want to test whether some divisor binomial is a factor of a given polynomial. More on that later.